I'm not a software guy, and I like to mess around with it though. And anyway, a while back I discovered these ESP32 development boards by Espressif, like it's already mentioned. And I thought, well, this is pretty cool. It's a step up from Arduino, it seemed like. So I ordered some up, and they're a pretty neat board. They come in 30-pin or 38-pin varieties. And the only difference really is the number of pins exposed. This is what they look like, and I've got the one in the project here I'm going to pass around. So anyway, I've been messing around with these for a while. Before the tariffs, they were $5 or $6, you know, in that price range. And you can program them pretty easily, it turns out, even for me. Here's some of the features. They have a surprising amount of memory, 34 programmable GPIOs, 10 of which can be touch sensors, and that's kind of a neat deal. 12-bit analog to digital converters and 2 digital to analog converters. Has a number of interfaces. I2C is what I've been using mostly, but I've also used some of the UART pins. It's got real-time clock, Bluetooth, Wi-Fi, and it's cheap. So programming, you can program it with Python or C. If you're comfortable with the Arduino IDC, it connects right up to that, and you can program away in that. Or if you want to use Python, I don't know how you pronounce it, Thorny or Thorny or whatever. That little IDE works really well from the standpoint that it lets you make the connection over the USB without any problem. So the connection is simple in both of those IDEs.
So you can just, from the Arduino, or from the Arduino IDE, just use the USB?
Correct. Correct. Yeah, you select the ESP board and yada yada, and
Yeah, you can select that from the Arduino?
yeah, and it just connects.
All
right. Anyway, so I've been messing around with it, and I wanted to do something to find out more about the Wi-Fi, and so I thought, well, let me do a little project where I connect to my home Wi-Fi, and then I'll send some data to the web and then get a response, and then put that on a display of some sort. So that was the objective, and this is kind of the result, sort of a little time and temperature project. I'll pass this around. You'll see the little ESP32 center stage there. I've got a little regulator circuit here so that I can plug it into my 12-volt bench supply. This is an external sensor on the back. I had it on the inside, but that didn't work out so well.
What does it sense?
It senses temperature and humidity.
Oh,
And so,
even humidity.
and then this is a 20 character by 4 line display. It's probably pre-tariff, you know, I don't know, not $20 worth of stuff here. So it was a pretty inexpensive project. You can't really see it here, but up at the top, it's got the day and the date. And then in this corner here, it's got wind speed and wind direction. And then below here is the time. And below that's indoor and outdoor temperature and humidity. So as a project, it's not very complicated. For the hardware, of course, there was the development board. I used a DHT22 sensor, which you can buy a bag of those for like $5 or $6. And then the generic display, and they were like, I think I paid like $7, and they come in green and blue and different colors. For the internet sites, for the weather information, I used Open Weather, and that's free as long as you don't ask them more than 1,000 times in a day for the data. And I don't. I update the data every 15 minutes or so. And then the NPT time server, which is, you know, that's what your computer hook gets the time from. And there are several of those that you can use. The software, you can hard code everything, but I decided to use a little JSON file, which is nothing more than a text file, and it's shown here. You put your Wi-Fi name in, and this is my Wi-Fi name I'm using, the password, and then when you sign up for Open Weather, they give you a key, and that's the key. And then you select your location. So for me, I type in Coon Rapids, Minnesota, and when I type in Coon Rapids, Minnesota, then it gives you back this number right here, and that means Coon Rapids, Minnesota. But it could be, it could be Paris, France, or whatever. It's anywhere in the world. And then I needed one little library. And that was for running the display. And this is what the library was called right here. So anyhow, then I went, and I'm not going to get into the code with you other than to give you the idea of kind of the order that I did it in. The first thing that you have to do is obviously connect to the Wi-Fi. Now, there's only about 3 lines of code that are required for this. Not too much. And so I've got a line that gets the SSID name and the password from the JSON file, and that plugs it in there. And then tell it to connect. And well, it connected about half the time. I said, what the hell is going on here? Well, it turns out that I was only giving it like a second or two to connect. And so I had to put a delay in there. And I put a 10-second delay in there, and now every time I ask it to connect, it connects. And I put a little line of code in there that displays connecting, Anyway. And then the next thing I decided to do was, well, I'd measure the indoor temperature and humidity. Now, this little sensor connects to only one GPIO pin on the board. It's you set it up and you tell it how often to get the data. And I thought, well, after messing with it for a little bit, I noticed that it changed, temperature really slowly. So I thought, okay, every 10 minutes would be plenty good, would know how warm it was in the house. And so then I put that in a little global variable so I could call it from another program, another part of the program. And then the part that I wanted to do was to connect to open weather. So I got a couple lines of code in there, say connect to open weather, and I have to send it my key and my location. And then it sends me back this relatively large JSON file. And in there's, wind speed, wind direction, temperature, dew point, humidity, the forecast. You got all sorts of things to choose from. Well, I only have a 4-line display, right? So I couldn't choose that many things. So I chose temperature, humidity, wind speed, and direction. And basically what you do is you parse that returned JSON file for those items, and then you can display them. And then finally, I needed to set the time. Now, the ESP32 has got a real-time clock, but it doesn't have a real-time clock battery.
Oops.
But that's not really a problem, because what I did was went out, and got the time. And once I got the time, then I set the RTC to UTC time. And then the next thing that had to be done was to adjust for the time zone. Well, we're 5 hours behind Greenwich Mean Time, and so that's easy enough. And then I don't like 24-hour time, so I wanted to convert the 24-hour time to 12-hour time, put a few lines of code to do that. And then I needed to determine, well, is it AM or PM? It's another couple lines. Determine the day of week, Monday, Tuesday, Wednesday. And then once that's all done, then display the data. So this is what I display. I display the day of the week, as in Monday, Tuesday, Wednesday, and then month, day, and year. And then I initially had it where I displayed hours, minutes, and seconds plus AM or PM. But more on that in a second. Then wind speed and direction in degrees, indoor temperature, humidity, outdoor temperature and humidity. And then if you want to display the seconds, you have to refresh the display every second, and that caused a little flicker in the display. And so I thought, well, if I got rid of the seconds, I wouldn't have to do that. So I did that. I got rid of the seconds, and that took care of that little problem. Now, interestingly, when I did this, I initially, just used a little breadboard and if you power everything off the USB connection, it all works. But the display has got a funky flicker to it, which goes away when you use an external power supply. So that's a little something to keep in mind. Now, so that was my little foray into figuring out how the Wi-Fi worked. And even for me, it was pretty simple. So if I can do it, you guys can do it too. And it's kind of fun because that opens up a whole bunch of things that you can do, you know. And it seems like everybody's got an API you can, you know, use. And so I'm slowly learning more about it. But I have really enjoyed using the ESP32. It's a fun device.
When you connect it with Wi-Fi, are you just getting weather from that, or what other information might you get?
Well, I'm getting the weather, and I update that every 15 minutes.
Okay.
So every 15 minutes I go out to that website and say, hey, give me the weather. And then initially, when I power it up, or if I hit the reset button on the back, I get the time from internet server time,
So, okay.
and set the real-time clock. And the real-time clock, once you set it, it keeps very good time. So I haven't had any problem. Well, although I have gotten a little RT real-time clock module with a little, you know, watch battery in it, that I'm going to add to this for, you know, backup.
Revision 2.
Yeah. But anyhow, that's how I kind of learned about the Wi-Fi part of it. Using it for standard GPIO, you know, switches and turning stuff on and off. That's real easy. It's just like with an Arduino. Now, I did all of this in Python, which is kind of my preferred over C, but you know, you can do all of this in C, obviously. No problem. Anyhow, that's one project. The other,
With Arduino, there's a base program in there, or data that makes the whole thing work, that you have to, if you're taking
Yeah, there's a
making
bootloader in there.
a 328 chip or 168 chip, they won't work with Arduino until you initiate it with.
Right.
Yeah.
How does this work?
You need a bootloader is what he's saying.
Yeah.
yeah. This will load a boot file onto the ESP32, but the file that runs when you power it up is always called main.py. So that's what you name it. So you can, whilst you've got everything hooked up to your IDE, you can have the file named anything you want. But once you want to pull the cord off and have it run by itself, then you have to name the Python file, you name it main.py.
Oh,
And-
like C.
Yeah, and whatever that's in that file, that's gonna run.
Okay.
Or in my case, not run. You know, but Yeah,
At a really low level, they're practically unbrickable. They've got a flash file system. You hold down GPIO 0 to ground when you power it up, basically, and it changes it into DFU mode, where you're basically writing into the flash. And so if you've got the Python code on it, yeah, then it'll run main.py. But if you want to run something in C or run the Arduino code or whatnot, you're basically holding that GPIO when you power it up, going to DFU mode. And does anybody know what DFU stands for? Is that like disk file utility
I
or something?
don't.
Basically, it just exposes a flash drive.
Makes it look like a flash.
You know,
drive.
over there, it makes it look
Drop
like a-
files in it, yeah.
Yeah. There are some interesting loaders that are web browser based too. So you can like compile your project and visit a website. And if you're using a Chrome based browser, so Microsoft Edge or Chrome or whatnot, you can right through the serial port on a laptop with nothing installed, just in a browser, you can write a project to it. But the whole TCP/IP stack and everything is all like burned into the hardware and abstracted. So the Wi-Fi connection, the radio, the Bluetooth radio.
But it has everything to compile whatever code you put into it. It sounds like C, having a main.
And the compiler stuff's all like external. So the Expressive makes a toolkit for communicating with the thing, and it's built into Arduino IDE, and somebody's written essentially or ported Python onto the thing. So if you want to call it a bootloader, you're putting an interpreter into it to understand Python code, or you're putting a loader to start your Arduino C code.
Yeah, you're putting a hex file in, but I think you know, on the Arduino, you've got the bootloader that you have to work with Arduino IDE. You gotta have that.
Yep.
And there's nothing like that in this?
It's not really, well, you'd have to have that, and most boards come with that in order to talk
Okay,
Arduino.
so it's there.
But then in Arduino, you used to have to load like
Yeah.
a boards library, and now for all the common boards, I think it's built into the latest versions of the Arduino IDE. So
Well,
if
you
you
could-
write with
you could always do it,
Arduino,
wasn't
you
it?
can just write to it. It's,
Yeah, all right.
in summary, they're really cool and really cheap.
And there's lots of development options.
Yeah, every
Interface
option, it
options,
seems.
so, yeah.
some months back, I brought in a receiver that I've been working on for probably 40 years now. And anyhow, I got to the part where I needed crystals for the down converter little modules, you know, and I couldn't find them anymore. I mean, I waited too long. So I thought, well, what am I going to do? You know, because I needed a frequency for 10 and 15 and 21, you know, to down convert the signal. So I thought, well, I need to go digital with this. So I thought, well, I can do better than the VFO that I built, which goes from 3.5 megahertz to 4 megahertz, but kind of drifts around a lot. And then I need 2 9 megahertz signals for upper and lower sideband. Then I need the down converters for, you know, the other bands. And so anyway, everybody that I talked to was, try this SI5351 from Silicon Labs, and they're cheap. So I ordered some up, and I'll pass this around. It comes without the connectors soldered on. I soldered on the connectors. Here. And Anyway, it's a really cool chip, and I really don't understand what I'm doing with it very well, but I have managed to actually get something done with it. It comes in three flavors. It comes in the A flavor, and the A flavor actually has, you can get it two ways. One with 3 outputs, which is the common one that you get on Amazon or AliExpress or whatever, or 8 outputs, which you can get on Amazon. Anyhow, this allows you, in the case of the board that I'm passing around, to have 3 separate clock outputs, which you can set however you want to set it. Then there's another flavor called the B, and the B adds an internal voltage-controlled oscillator that you control externally. I know nothing about that. I'm just telling you that this is what the spec sheet says. And it has 8 outputs. And then the C, which I haven't seen available on a development board yet, but you can buy it through DigiKey or whatever, that can synchronize to an external clock. So if you've got, GPS discipline clock or something like that, you can sync it to it. So it's pretty versatile, and for what I've been doing, it's really cheap. Now this is the A right here, and all of them come with a 25 megahertz crystal. So that's the crystal that's running to power this thing up. And this chip here that has the 3 outputs is a 10-pin chip. It's it's a little tiny thing, you know. I got a solder blob on it, and I had a hell of a time removing the short. Anyhow, but they all are controlled by I²C. And depending on the flavor that you've got, you have the ability to select one of 2 I²C addresses based on whether you pull a pin high or low. Also, this is kind of neat, and I will never use this feature, but the A version and the B version can do spread spectrum. And if you read the data sheet, and it's pretty comprehensive, it shows you how to do it, although I don't think my math skills are probably up to it. But anyway, as mentioned, it's controlled via I²C, so that's real easy. That's 2 wires, clock and data. And then you can hook it up to all kinds of devices, like an Arduino, an ESP32, a Raspberry Pi, and there are quite a number of libraries available. However, most all the libraries that I have come across are for doing your program in C. So that's something to keep in mind.
And what's the nature of the signals you're sending over the I2C?
Just data and clock. It's about 400 kilohertz is the speed of it. It's slow.
Yeah.
It's slow. So the 2 signals that you send, the clock and the data, 2 different lines, they're basically saying divide by this number or divide by that number. They're,
So are these, this instruction set, is it explicit in the manual?
they're instruction sets they're instructions that are part of the code in your program that you send to the
Yeah, that you sent through the I2C. What I'm wondering is, what is it you're writing down?
You're
Make
loading
sense,
registers into
change
chip,
frequency
basically.
or whatever.
Yeah, you're writing values into registers in the chip.
So what?
You're right. Hold that thought for just a minute, Mike.
Okay.
Just hold that thought for a minute. So anyway, this is a very broad stroke because I don't pretend to understand everything about this by any stretch of the imagination. But anyway, I thought, well, let me poke around. So I spent a couple of days looking on the internet for, various projects. I went to Project Hub and Hacker.io and, all over the place. And I thought, let me find somebody's code that's done this so that I can get an idea of how they went about controlling this chip. Because
That's what I want.
I had no idea where to start.
Yeah.
Okay, so anyway, I found some stuff and I breadboarded it out. And then I made this little module, and I'll pass this around. You'll see it's got the little development board. This is an Arduino Nano.
Okay.
And so it's in C. This program is in C. And then this is a little OLED display.
Oh.
And then this is a rotary encoder with a little push switch on it.
And your frequency and whatever is on.
Frequency shows up here. You can't see it there, but it's showing 7 megahertz.
Okay.
But yeah, it's pretty accurate. I've got a counter that's GPS disciplined, and I would say that this is within a couple hundred hertz at the outside. But I wanted something. I wanted something that I could mess around with, and
Yeah.
so this all is on sockets. So I put it all on sockets, and at some point, I don't like these little displays, so at some point I'd like to make a nice, larger display. I've got a Nexiton or I don't know what they call those things, but it's a 4-inch display, and it allows you to program it and then control it over I2C, and I'm hoping to figure that out. But anyway, I'll pass that around.
So who makes the libraries that you're using to?
There were 4 different libraries that I had to include. Yeah.
Okay, and where did they come from?
GitHub. They're all on GitHub.
Oh.
And so that's where I found the libraries.
SI5351 libraries?
Yeah.
Okay.
And when I was looking around and looking at what other people did, I looked at what libraries they used as well.
Okay.
So I will say that the code that's in there is not all my code. All right. So
Hope not.
yeah. Anyway, here's kind of a
Yeah.
I've got a little regulator, I've got 12 volts, not 13.8, but 12 volts on my bench. And so, that's at the top end for the Arduino, so I put a 9-volt regulator on the board. This is the Arduino Nano. I've got some version 3s. This is the rotary encoder, and the rotary encoder needs some pull-up resistors and stuff, you know, and a couple of capacitors. This is the actual SI5351 board, and this is the little display. And as you maybe can't see it, but they both hook to the same I2C line. So anyway, that little device right there will give me an output from about 100 kilohertz up to about 150, 60 kilohertz.
Oh,
And,
Kilohertz or megahertz?
pardon?
Kilohertz or megahertz?
About 100 kilohertz to about 150, 60 megahertz.
Oh.
Now, the board says it'll go from 8 kilohertz to 170 megahertz, but I don't know. Anyway,
no problem with the HF band.
yeah, no problem with the HF band, no. Now, unloaded, you get about a technically a 3.3 volt peak-to-peak signal. And it's a square wave, so, you know, you're gonna have to put a filter on it to, you know, make it work in a radio. With a 50 ohm load applied, it drops the output to 0.6 of a volt peak to peak.
Which power output were you using on the board though?
You mean, okay, so 20 milliamps. Excuse me. Now I can't remember, but I remember this much. The board can be set for 3 current level outputs.
It's like 2, 6, and 8 or something like that.
Yeah, something like that, yeah. And I'd have to go back and see, I don't remember.
It's adjusted.
But anyway, I like using a 50 ohm load on it, so if you saw there was a resistor soldered on, and that's a 50 ohm resistor.
So with a 50 ohm load, you drop from 3.5 volts to 0.6 of a volt?
Correct. And then, so anyway, that's my little project in C. And then I thought, well, I really would like to do this in Python, because what I'd like to do is I'd like to have use like a Raspberry Pi 2W or something like that to control everything in the radio. So I thought, well, let me try, you know, controlling this with my Raspberry Pi. So I hooked it up to my Raspberry Pi 5, and, you know, this is all that you need. You've got power, ground, and the I2C bus connection. And now, I haven't gotten near as far with Python as I got with C. So you might wonder, well, if I'm going to try this, what's involved? Well, we already mentioned that the thing's got a 25 megahertz crystal on it. And there are 2 PLLs. And each of these PLLs are multiples of the 25 megahertz clock. And they can be either an integer or a fractional multiple of the 25 megahertz. But the multiple must be between 15 and 90. So I'll give you an example here. Let's take 25 megahertz times 20, right? That would equal 500 megahertz. Now, that actually is very simple to send over the I2C to the board. And to your point earlier, Mike, when you're sending data, this is the kind of data that you're sending. You're saying, okay, to the register, I want you to divide by 20 or whatever it is. And if you're going to divide by a fractional amount, then that gets a little more complicated. There are two PLLs you configure, and they don't have to be configured the same. You can configure one way and one another way. And there's also, because the final, well, let me go one step further. After you configure your PLLs, then you have to configure, in the case of this little board, clock 0, clock 1, clock 2. Now, how do you do that? Well, let's say, for example, PLL1 was set at 500 megahertz, and you want a clock output of 10 megahertz. Well, then you would have to divide 500 by 10, right? And that would, and that would give, excuse me, you would have to divide by 50 to get 10 megahertz out. Now, if you want something other than a very even number, now you've got some computation to do.
Why did you go up to 500 megahertz before you started?
Well, because you have to multiply the 25 megahertz crystal by some number between 15 and 90.
Okay, that's.
Yeah.
And
So-
all your output clocks are divided from that 500.
Correct.
Okay.
Now, Silicon Labs had apparently at one time something called a clock builder, which lets you plug in what you wanted and it would do all the arithmetic for you. I tried to find that program, and I did find Clock Builder Pro, which got sold off to some company called Skyworks, and it does all that stuff, but then you have to buy their development board and pay them money. I couldn't find this thing that the early bloggers were talking about, so I was SOL on that. So obviously, fractional divisors are needed from a practical standpoint, and that's where things get complicated. And there is, you may want to change your PLL divisor rate on the fly and things like that. And I am not prepared to speak to that at this point, other than I know that, you know,
It's a whole science / black magic.
it is. And that's what I'm trying to figure out using Python. So, like I said, I can do some simple stuff in Python, but I haven't figured out how to get, you know, the more complicated stuff accomplished. Anyway, essentially, after you've got your PLL and your clock division rates set, figured out. Then you have to decide how do you want to control this on the fly. Do you want like a rotary encoder? Do you want some push buttons? How do you want to do that? You got to do that. And then you need some kind of a display. Now, whilst I'm doing this stuff in Python, the display is easy because it shows up in the terminal. It says, the frequency is X. And I can verify that with my frequency counter. Unfortunately, if I'm over 100 megahertz, I have to rely on my frequency counter because my scope only goes up to about 90 and then it peters off real fast. But so that's kind of what's involved. Now, if you are just looking for a little project to make a single output, like for a signal generator or whatever, QRP Labs has got the code on his site that you can download and make yourself a really nice little generator, and then he's got the little bandpass filters that you can buy from him, and they'll take that square wave and smooth it out real nice, and all of that, and you can do that for cheap. And it's very accurate.
But he provides the code that you need to do your frequency calculation.
He does have a sample that works. He has a sample that works, and his displays on a display for my little weather, time and weather thing. He doesn't display it on a nice LCD or anything.
Well, he's done some nice stuff with some of his receivers and transceivers.
Oh, yeah. Yeah, and you could take his code, and if you didn't like his display, you could, with not too much effort, you could port it over
code
to.
that you can go in and
Yes,
well commented.
it's pretty well commented, yeah. And he's not the only one. There's a couple others that I found on the web. There's one guy, and I was going to try this, but I didn't. I just ran out of gas. He made a generator that had an awesome display. It mimicked an old-fashioned analog display, but it used an LCD display for it. And there's a video of it, and it's really neat. But anyway, and he's got all the everything there, the code and the parts and that you need and everything. And that would be kind of cool to try. But anyway, this is my little foray into learning about the 5351. And by the way, there's a whole family of these chips. This is just the one that happens to be, available to the do-it-yourself community, and cheap, and on a development board. So hopefully down the road I'll make some progress on my receiver, and I'll have more to explain about how you talk to this chip.
So on all your IF stages, you'll have a 5351 signal generator to mix with the signals to bring them to change your IF.
Well, what I'm hoping for is using just one of those boards, one output, clock A for the VFO.
Yeah.
Clock B is going to be a down converter
Right, okay.
that as I switch you know, whatever the switch is that tells the micro, hey, go to this frequency. And then the third output is going to be for a 9 megahertz signal that will be either a little above or a little below 9 megahertz for my upper and lower sideband. So that's the goal. Whether I achieve it is
Hope you
another.
live long enough.
Yeah, yeah. So, but I would encourage you guys to try it if you've been, if I can get something to work, anybody can get it to work, because I am not a software person. So that's all I got.